So logarithms are powers. And powers have to go with bases. So as we saw with the indices, you can't have a power without something to raise it to. So if I find logarithm of 3 to the base 10, that means the base that's involved with this power is 10. So on your calculator, you've got a button. That's the log button. LOG is written on it. It doesn't have the 10, but it's implied that the base is 10. So that button on your calculator gives you the power of 10. If I find the logarithm to the base 10 of 3, and what does that turn out to be? You give me about 6 significant figures. Thank you. That's the power of 10 that gives 3, 0.477121. So in other words, to check that, therefore, 10 to the power 0.477121 should equal, and it won't exactly because you've rounded it, it's rounded it for me, it should give round about 3. And it's no coincidence that the 10 to the power button is above the log button. So shift log will give you 10 to the power. And that's because the logarithm gives you the power of 10, so they're inverse functions. So I can turn a number into a power, and in this case using that log button to the power of 10. I can turn any number into a power of 10. In this case, a power of 10. So I'll put 10 in brackets because it could be any base. I can actually have got some calculators have got the button to allow you to do any base, but we tend to stick to 10s. The point is that we can turn a number into a power. You might wonder why we turn a number into a power of 10, for example. So I can turn 3 into a power of 10. The logarithm of 3 is 0.477121. I do that because then I can use the laws of indices in a way that we've looked at. I go back to the laws of indices, which are up here. These are to do with powers. So long as the base is the same, so if we think back to the logarithms you've just been looking at, that button on your calculator gives us a common base of 10. So long as the base is the same, I can turn a multiplication into an addition using the first law of indices. So if I turn a number into a power, I can, instead of multiplying the numbers, I add them together. A division can become a subtraction. And so we end up with the laws of logarithms, which are here. Instead of doing a multiplication, multiplying A and B together, I can actually find the log of A and the log of B and add them together. So the first law of logarithms comes from the first law of indices. Multiplication becomes addition, and similarly division becomes subtraction. So there are 3 laws of logarithms, and do you remember me saying at the start you might want to write them with the laws of indices so you've got them together. Wherever you wrote those laws of indices, it might be worth writing that with it. The really interesting one is the last one. And that's the reason why we're focusing on these laws of logarithms now. This last one means that we can turn one power, remember logarithms are powers, so a power raised to another power becomes a multiply. And that's the useful one. And that comes from that third law of indices, which if we think back to it, is here. 1 power, a to the n, raised to another power, gives us a to the n times n. So we turn 1 power raised to another power into a multiplication. And that's what the third law of logarithms is saying effectively here. We can turn a power into a multiplication. And that's where it starts to get useful, because it allows us to solve equations where the unknown is in a power. And so I want to look at some examples of those. So when you've made a note of that, let's look at an example. Again, in the textbook, this problem is in the textbook, so you don't need to write this down. It's written out there for you. You might want to, because I'll probably do it a slightly different way. And it's on roughly page 100, I think, in the textbook, where those laws of indices are, maybe a bit further on. So, solve the equation 2x equals 3, correct to 4 significant figures. What I do is, because x is in the power, I take logarithms of both sides. This is an equation, 2x equals 3. Whoops, 2 to the power x equals 3. If it was 2x equals 3, it would be easy. 2 to the power x is 3. As soon as I see my unknown, my x is in the power, logarithms comes to mind, or should do. Like any equation, so long as I do, if I want to do something to one side, so long as I do it to the other side, I've not changed the equation. To get this power down and turn it into a multiply, I use the third law of logarithms that we just looked at and say that the logarithm of 2x to 2 to the power x equals the logarithm. And I'm just using a different colour to emphasize that we're doing the same thing to both sides. I'm finding the logarithm, not stated but implied that it's to the base 10, because logarithm to the base 10 is just written as logarithm. So the base is 10. Logarithm of 2 to the x equals the logarithm of 3. And now we can use this third law of indices, which says that that n, which is in the power here, can come down and become a multiply. So I can get my unknown, which was in the power, down, and it becomes a multiply. So in other words, x times the logarithm of 2 equals the logarithm of 3. And now we've just got x multiplied by a number. The logarithm of 2 is a number. We could work out what that was on the calculator. It's just a number. So divide both sides by the logarithm of 2 to get x on its own. The logarithm of 3 divided by the logarithm of 2. And now we reach for the calculator and work out what that is. So we work through this problem. Because I've used the laws of indices, I can bring the x down and turn it into a multiply, which is here. It's worth recapping it anyway, which means that now it's like a straightforward equation. I can divide both sides by log 2, so x equals 1.585. And as a check, put the numbers in and it works. Okay? Okay, so for this one, solve this equation. 2 to the power x plus 1 equals 3 to the power 2x minus 5. Again, what I'm after, x is in the power. So as soon as I see that, logarithms comes into mind. So 2 to the power x plus 1 equals 3 to the power 2x minus 5. And if you're writing this, make sure it's obviously in the power, otherwise you'll make errors. So now I can write the logarithm of 2 to the power x plus 1 equals the logarithm of 3 to the power 2x minus 5. And because I've turned this into a power, I can bring the x plus 1 and the 2x minus 5 down and turn them into multiplications. So once you're used to doing these things, you can actually miss out this intermediate step here and go right straight to this equals x plus 1 times the logarithm of 2 equals 2x minus 5 times the logarithm of 3, because of that third law of logarithms. That power can come down and become a multiply. At this point, I could multiply out the brackets. But remember, log 2 is a number, and we want to hold that number to 4, 5, 6 significant figures. So if I were to multiply out this bracket, and I have quite long decimal numbers in here, it would work, but the accuracy might suffer a bit, and it would certainly be a bit more difficult to work with it. So what I could do is to divide both sides by log 3 to get rid of the log 3 on this side, or divide both sides by log 2 to get rid of the log 2 on that side. And then I'll just have one number with lots of decimal places in them. Which way to go? Well, I've got to remember that I'm going to multiply out the brackets. So this awkward decimal number multiplying out with this will probably be a bit easier to work with because it's only x plus 1 rather than 2x minus 5. So making life easy for myself, I would probably decide at this stage to divide both sides by log of 3 to get all these awkward numbers together on the left-hand side. So that tells me that x plus 1 times the logarithm of 2 over the logarithm of 3 equals 2x minus 5. And now I work out what log 2 divided by log 3 is. (0.631) times x plus 1 equals 2x minus 5. So now I am going to have to multiply out the brackets. 0.631x plus 0.631. Maybe you can see now why it's best to go that way. It's easier to work it out. Equals 2x minus 5. And now I try and get all the x's on one side of the bracket and all the one side of the equation rather, and all the numbers on the other side. So I'm going to subtract 0.631x from both sides to get rid of the 0.631x over there. And I'm going to add 5 to both sides to get rid of this minus 5 over here. So let's do that in 2 steps. So subtracting 0.631x from both sides, I get 0.631 equals 2x minus 0. What's 2 minus 0.631? 1.369 x minus 5. Add 5 to both sides. 5.631 equals 1.369x. And now finally divide by 1.369. And we've got x. And that turns out to be so 4.1 to 2 significant figures, which I think is what the question asks for. So 4.1. How do we check? We would put that value for x back into the original equation and see whether or not, if I work out what 2 to the power 4.1 plus 1 is, and what 3 to the power 2 lots of 4.1 minus 5 is, and see if I get the same answer. If you're in an engineering situation, you need to be able to check you've done it right, and that's the way to do it. Okay, so look now in the textbook, page 100 ish, Laws of Logarithms. I want to move ahead in here although it's interesting in its own right to play around with these logarithms, I don't want to look at this particularly. And what I wanted to do is to move to the section on indices equations, which is on page 103. And you'll see on there the problems that we've just been looking at, problem 23, so we agree 4.1 to two significant figures. There's another work problem that you could look at on page 403, and then exercise 54. So